Hello to all my viewers. This is Dr. Dhaval Maheta, and today we are going to discuss how to run two-way MANOVA in SPSS. A two-way MANOVA, that is multivariate analysis of variance, is an extension of ANOVA that allows researchers to examine the influence of two independent variables on multiple dependent variables simultaneously. Some basic requirements for running two-way MANOVA are: it requires two independent variables on the scale of nominal or ordinal, that is discrete, and two dependent variables on the scale of interval or ratio, that is continuous. Before we proceed further, let us understand the family of ANOVA. We start with basic ANOVA. Basic ANOVA consists of one dependent variable, one independent variable, and zero covariates. So here, the independent variable is level of education, discrete. So we are having postgraduate, graduate, and undergraduate. Dependent variable is test score, continuous. Our objective of the study is to study the effect of level of education on test scores. Next is ANOVA. One dependent variable, one independent variable, one covariate. So the independent variable is same, dependent variable same, but one more additional variable has been included in our study, which is number of hours spent on studying. This is covariate. So we want to control the effect of this variable on the dependent variable. Basically, we want to kill its effect. So that's known as covariate. The next is one-way MANOVA. One independent variable, two dependent variables. Independent variable, of course, in discrete. Dependent variable, continuous. So you can see a test score was already there, and another dependent variable has been added, which is annual income. So the objective can be to study the effect of level of education on test score and annual income. In previous case, in ANOVA, our objective can be to study the effect of level of education on test score, controlling the effect of number of hours spent on studying. Next is two-way MANOVA. Two dependent variable, 1, 2. Two independent variable, 1, 2. So this we are going to do today. Zero covariate. So independent variable affecting dependent variable, test score and annual income. Gender affecting test score and annual income. And one more objective is to study their interaction effects. So let's start with the first objective, to study the effect of level of education on test score and annual income. First objective. Second objective, to study the effect of gender on test score and annual income. The third objective, to study the interaction effect of level of education and gender on test score and annual income. Next is MANOVA. Two dependent variables, one independent variable, and one covariate. So we want to control the effect of this. The objective is to study the effect of level of education on test score, annual income, controlling the effect of number of hours spent on study. Real life applications of two-way MANOVA are: for the healthcare, researchers might study the combined effect of different medications, that is the types of drugs, and patient demographics on multiple health outcomes such as blood pressure, cholesterol levels, and weight. Education. In the learning environments, assessing how different learning environments, that is classroom vis-a-vis remote, and teacher experience level affect student engagement, comprehension, and retention. Business and marketing. Evaluating the effectiveness of different advertising strategies, example social media versus traditional media, and market segments, example the age groups, on multiple marketing metrics like brand awareness, purchase intention, and customer loyalty. Psychology. Studying the effects of different therapy techniques, example cognitive behavioral therapy versus psychoanalysis, and patient characteristics, example age, gender, on psychological outcomes such as anxiety levels, depression scores, and overall well-being. Environmental science. Assessing the effects of different pollution sources, example industrial versus vehicular, and geographical locations on multiple environmental health indicators such as air quality, water quality, and soil contamination. Sport science, examining how different training programs, example strength versus endurance, and athlete demographics, example age, gender, affect multiple performance outcomes like speed, strength, and endurance. Sociology, analyzing the impact of different social programs, example welfare versus job training, and demographic factors, example age, education level, on multiple social outcomes like employment rates, income levels, and quality of life. Agriculture, assessing the impact of different farming techniques, example organic versus conventional, and environmental conditions, example rainfall and temperature, on multiple crop yield parameters like growth rate, yield quantity, and quality. Assumptions of two-way MANOVA are independence of observations. Observations within and between groups should be independent of each other. This assumption ensures that the data points are not influenced by each other and that each observation provides unique information. Multivariate normality. The dependent variable should follow multivariate normal distribution within each group. This means that for each combination of the group and dependent variable, the data should be normally distributed. Linearity. The relationships between the dependent variable and the independent variable should be linear. MANOVA assumes that the relationship between the independent variable and the dependent variable is linear. Homogeneity of variance covariance matrices, homoscedasticity. The variance covariance matrices of the dependent variable should be equal across all groups. This assumption implies that the spread, variance, and the shape, covariance of the data distributions should be similar across groups. This can be tested using box M test. Sample size. Generally, there should be more cases in each group than the number of dependent variables. A common rule of thumb is that the sample size in each group should be at least larger than the number of dependent variables. Multicollinearity. The independent variable should not be highly correlated with each other. High multicollinearity can inflate standard errors and make it difficult to interpret the results accurately. Now let's take one case study. A researcher is investigating how different types of medicine and gender influence health parameters. So independent variables are medicine and gender. So you can see here medicine, gender, systolic blood pressure, pulse rate, oxygen levels. The study involves two independent variables, medicine and gender. The dependent variables measuring health outcomes are systolic blood pressure, pulse rate, and oxygen levels. Data were collected from 20 patients who were randomly assigned to one of the three medicines. The multivariate hypothesis which we want to test is, we start with the effect of medicine. There is no significant effect of medicine on the combined dependent variables. The combined dependent variables are systolic blood pressure, pulse rate, and oxygen levels. Effect of gender. There is no significant effect of gender on the combined dependent variables. Interaction effect. This I had already explained in the previous slides. There is no significant interaction between medicine and gender on the combined dependent variable. So this is multivariate hypothesis. Next is univariate hypothesis for medicine. This is for medicine and this is for gender. Null hypothesis. There is no significant effect of medicine on systolic blood pressure. Effect of medicine on pulse rate. There is no significant effect of medicine on pulse rate. Oxygen levels. There is no significant effect of medicine on oxygen levels. Now, the next hypothesis is for the gender. There is no significant effect of gender on systolic blood pressure. Next, for pulse, there is no significant effect of gender on pulse rate. Next, on oxygen level, there is no significant effect of gender on oxygen levels. Univariate hypothesis for interaction effects. This is just a hypothetical example for the learning purpose. So the interaction effect, medicine and gender on systolic blood pressure. There is no significant interaction effect between medicine and gender on systolic blood pressure. Next, for pulse rate, there is no significant interaction effect between medicine and gender on pulse rate. Next, for oxygen level, there is no significant interaction effects between medicine and gender on oxygen levels. Now, so this is your data. Now we'll go in analyze, generalized linear model, multivariate. I'll transfer systolic blood pressure in the dependent variable, pulse rate in the dependent variable, oxygen level in the dependent variable. This should be on continuous scale, that is ordinal or ratio. Sorry, not ordinal or ratio, ratio or interval. Now transfer medicine into the fixed factor, gender into the fixed factor. This should be discrete. This is a categorical data. This is continuous data. So this can be on nominal or ordinal scale. This should be on ratio or interval scale. Let's proceed further. In model, no changes, keep as it is. Make sure type 3 is on. Contrast, no change. Plots, transfer medicine on the horizontal axis, add. Transfer gender on horizontal axis, add. Now transfer medicine on horizontal axis, gender on separate lines, add. And then press continue. Post-hoc. So transfer medicine here, transfer gender, activate Tucky's test, continue. Estimated marginal means, we want the estimated marginal means for medicine, gender, medicine and gender, activate compare mean effects. So here we are having two tests. One is LSD none and another is Bonferroni. So LSD is a least significant difference. It is used when you want to find the significant difference between the pairs. But when you are sure that there is a possibility of type 1 error in this pairs, so you go for Bonferroni. So I'll activate Bonferroni test, continue. In save, nothing to do. In options, activate descriptive statistics, estimates of effect size, homogeneity test, continue, click OK, and the results are ready. So we'll start first with the Levin's test of equality of the error variances. Right click, copy. So let's do the interpretation. We will have to see the p-value. So for systolic blood pressure, pulse rate, oxygen levels, the p-value for all the variations of Levin's test are much greater than 0.05, indicating that there is no significant difference in the error variances across the groups. Thus, the assumption of the homogeneity of the variances for systolic blood pressure, pulse rate, and oxygen level is met. So this is desirable, that the p-value should be more than 0.05 and we get the equality of the variances. That is, the homogeneity of variances is established. Next, we have to check for the covariance matrices. This we will get it from here. Yeah, here is it. So right click, copy. What is our null hypothesis? The covariance matrices of the dependent variables are equal across all the groups. Now just see the p-value. As the p-value is greater than 0.05, we fail to reject null hypothesis. So in the layman, you can just remember accept, but don't write it in the paper. Or normally we write we fail to reject only. We fail to reject the null hypothesis. This means that we do not find statistically significant difference in the covariance matrices of the dependent variable. This is desirable among different medicines and gender. Thus, the assumption that the covariance matrices are equal across groups, that is, the homogeneity of the covariance matrices, is not violated based on the result of box test. The next is the multivariate test. So this table I can get it from here. Yeah, here is it. Right click, copy. Okay, let's start with the interpretation. We will have to focus on the p-value and the partial eta square. As a p-value of the medicine, this one is 0.00. So all of them are having the value less than 0.05, which is less than 0.05. So the result indicates that the different medicine has a significant effect on the important vitals of the patients. The model is a good fit for the data, and the effect size, the partial eta square, this one, ranges from 0.510 to 0.864, indicating moderate to strong effects of medicine on the dependent variable. Next, we'll do the interpretation for the gender. See the p-value. All of them are having the value more than 0.05. So as the p-value of the gender is more than 0.05, so the result indicates that the gender does not have a significant effect on the important vitals of the patients. The effect size is 0.398, indicating a small effect of gender on the dependent variable, but it is negligible. We cannot consider it as the p-value is more than 0.05. It's insignificant. Let's proceed further. So this is interaction term, medicine into gender. See the p-value. All of them are having the value more than 0.05. Let's write the interpretation as the p-value of the medicine with gender, the interaction term, is more than 0.05. So the result indicates that the interaction of gender and medicine does not have a significant effect on the important vitals of the patients. The effect size, this one, the partial eta square, ranges from 0.172 to 0.282. Very small effect is there, indicating a small effect of the interaction term on the dependent variable. Next is test of between subjects effects. So in medicine, see here it gives the overall picture, but here if the effect is there, then the medicine is affecting what? Systolic blood pressure, pulse rate, or oxygen level. So that's the reason we go for test of between subjects effects. This table, I will get it from here. Yeah, here is it. Right click, copy. Okay, let's do the interpretation. Let's focus on the p-value. As the p-value of the systolic blood pressure, pulse rate, and oxygen level. Actually, here it should be 0.009. Let's change it. Is less than 0.05 for medicine. So the result indicates that the different medicine has a significant effect on systolic blood pressure, pulse rate, and oxygen level, as the p-values are less than 0.05. Now let's see for gender, as the p-value of the systolic blood pressure, pulse rate, oxygen level is more than 0.05 for gender. So the result indicates that the gender does not have a significant effect on systolic blood pressure, pulse rate, and oxygen level. Now let's see for the interaction term. Medicine with gender, as a p-value of systolic blood pressure, this one, pulse rate, and oxygen level is more than 0.05. So the interaction term, so it indicates that the interaction term does not have a significant effect on systolic blood pressure, pulse rate, and oxygen levels. The next, we'll go for post-hoc test, the pairwise comparison. So systolic blood pressure is affected by which medicine? So 3 medicines will be compared. It's a pairwise comparison. So we want to get this table and this plot. This will be available here. See, pairwise comparison. Here is it. And the plot will be available here. Yeah, here is it. So this is for medicine, systolic blood pressure, medicine, then pulse rate, medicine, then oxygen level, medicine. Similarly, you will get it for gender also. Systolic blood pressure according to the gender. Next, you will get pulse rate according to the gender. Here is it. Then oxygen level according to the gender. Here is it. Then you will get the graph of interaction, systolic blood pressure, medicine and gender. Okay. Pulse rate, medicine and gender, and oxygen level, medicine and gender. Now let's see the interpretation. Just see the p-value. Medicine A compared with medicine B, and the p-value is less than 0.05, and the difference between these two, that is a mean of systolic blood pressure of those patients using medicine A minus mean of those patients, mean systolic blood pressure of those patients using medicine B. The difference is negative. It means that the medicine B, those patients which are using medicine B has a higher systolic blood pressure, and the difference is minus 9.8, and the p-value is less than 0.05. It means the difference is significant. When we compare A with C, the difference is 2.708, and the p-value is more than 0.05, so we can say that difference is not so significant. Now you compare A with B or B with A, the difference is only of the positive, negative and positive sign. The p-value remains the same, so there is no point in comparing it again and again. So A with B, A with C, and B with C will serve the purpose. Now let's write the interpretation. So on the basis of this, we are having a graph here, medicine A, B, and C. Okay, as the p-value of some pairs is 0.00, which is less than 0.05, so that there is a significant difference in systolic blood pressure according to the medicines. So if the difference is there, then it is between which pair? So A compared with B, the p-value of this pair is less than 0.05. So the difference is significant. This difference, medicine A results in a significantly lower systolic blood pressure compared to medicine B. Okay, how much it is less? Minus 9.833. A with C, the p-value of this pair is more than 0.05, so the difference is not significant. B with C, the difference is 12.542, p-value less than 0.05. The p-value of this pair is less than 0.05, so the difference is significant. Medicine B results in a higher systolic blood pressure compared to medicine C. Now we'll compare pulse rates. So A with B, difference negative, p-value more than 0.05, not significant. A with C, p-value more than 0.05, difference not significant. B with C, okay, the p-value is less than 0.05. I will write the interpretation. As the p-value of some pairs is less than 0.05, so that there is a significant difference in pulse rate according to the medicine. The p-value of the pair A and B is more than 0.05, so the difference is not significant. A with C, the p-value of this pair is more than 0.05, so the difference is not significant. B with C, the p-value of this pair is less than 0.05, so the difference is significant. Medicine B results in significantly higher pulse rate compared to medicine C. Next, the oxygen levels. A compared with B, p-value less than 0.05. A with C, more than 0.05. B with A is same as A with B. Okay, B with C, p-value less than 0.05. So as the p-value of some pair is less than 0.05, so there is a significant difference in the oxygen level according to the medicine. A with B, the p-value of this pair is less than 0.05, so the difference is significant. A with C, the p-value of this pair is more than 0.05, this one, so the difference is not significant. B with C, the p-value of this pair is less than 0.05, so the difference is significant. Medicine B results in significantly lower oxygen levels compared to the medicine C because the sign is negative. Now let's see the pairwise comparison. So basically we are talking about systolic blood pressure, female, male, male, female, according to the gender. So we want to do the comparison here. Just see the p-value. So systolic blood pressure according to male, female, pulse rate according to the male and female. Just a minute. So the oxygen level according to the gender. Now the p-value of all these pairs is more than 0.05, so we can say that the difference is not significant. I will write the interpretation as the p-value of all the pair is more than 0.05, so there is no significant difference in systolic blood pressure, pulse rate, and oxygen level according to the gender. Next is the interaction effects. So systolic blood pressure, medicine, male, female. So these are their mean values. Pulse rate, medicine, gender, oxygen levels, medicine, and gender. Now, the interaction effects were not significant, but still you can put this in the paper. This is basically the plots for the interaction effects. Conclusion: for medicine, systolic blood pressure. The type of the medicine significantly influences systolic blood pressure. So as the p-value was less than 0.05 for some medicine. Specifically, medicine A significantly lowers systolic blood pressure compared to medicine B, while medicine B significantly increases systolic blood pressure compared to medicine C. There is no significant difference between medicine A and medicine C. Pulse rate. Medicine type also significantly affects pulse rate. Medicine B results in significantly higher pulse rates compared to medicine C. However, there are no significant differences between medicine A and medicine B, or between medicine A and between medicine C. Oxygen levels. Medicine type significantly impacts oxygen level. Both medicine A and medicine C results in a significantly higher oxygen level compared to medicine B. But this difference is not so significant. There is no significant difference in oxygen levels between medicine A and medicine C. Conclusion: for gender does not have a significant effect on systolic blood pressure, nor there is a significant interaction between medicine type and gender. Pulse rate. Similar to systolic blood pressure, gender does not significantly impact pulse rate, and there is no significant interaction between medicine type and gender. Oxygen level. Gender does not significantly affect oxygen level, and there is no significant interaction between medicine type and gender. Implications of this research. The significant differences in systolic blood pressure, pulse rate, and oxygen levels between the medicines imply that the healthcare providers can make more informed decisions when prescribing the medication. For instance, if lowering the systolic blood pressure is a priority, medicine A or C would be more suitable than medicine B. The next is the lack of significant gender differences suggests that the effect of medicines on systolic blood pressure, pulse rate, and oxygen levels are consistent across male and female patients. This consistency allows for the uniform treatment protocols, reducing the need for gender-specific medication adjustments. Next is healthcare providers can prescribe these medicines without needing to extensively modify dosages or treatment plans based on gender, simplifying the prescribing process and ensuring equitable treatment for male and female. So this was all about how to run two-way MANOVA in SPSS. For more videos on advanced data analysis using SPSS, kindly subscribe to my channel. You can also refer my playlist in which I uploaded videos on data science, machine learning, and artificial intelligence. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.